Cinzia
Yes.
is giving the talk. Multiparty reactive sessions. Please
Yes.
go ahead, Cinzia.
So thank you very much. And so I'm talking about sessions. I will assume a lot of things since the community is an expert in sessions. So if I say something that you don't understand, that is not familiar, please raise your hand and feel free to interrupt me. So we all know what session types are, and so we need to codify this structure of communication, but usually there are some ingredients that can be missing. So there are a lot of flavors of session types, and we, in particular, we focus on the need of what do we do if we want to broadcast something, what do we do if we have some signals that come, so how to react to those signals, and how to take care about time. So there are a lot of approaches that talk about physical time, and instead we went to a new programming setting, so synchronous reactive setting, that embeds broadcast, events, and concerning time, we talk about logical instance. So let me just give you a very brief introduction of what is a synchronous reactive programming. So we have a sort of logical tick that marks time, but it's not physical. So in this setting, we have that components are computing till they can't do anything more, so they are suspended. I will say what can they do and why they are suspended, so just follow the intuition now. And when they are suspended, then they pass to the next instant. And they are synchronous in the sense that they all pass to the next instance together, and they react simultaneously to events that can be emitted during the logical instant. And there is a new kind of property that is similar to progress. So we say that we can compute, so there is no deadlock, there is no, infinite loop inside a logical instant. So we can prove that each instant will terminate, will arrive to a suspended point. So what is the marriage between the two then? So it is reactivity and sessions. So first of all, we want that all requests coming from participants must be answered within the same logical instant. And the second thing that we want to have, we want to be able to react to events and try to execute an alternative protocol when we recognize that an event has been emitted. So again, some intuition on how a logical instant works in the session setting. So as I said before, we have these components, these participants, that they will compute until they cannot evolve anymore. So when they cannot evolve anymore. So we say that each participant can broadcast at most once. So if we have two send actions that are consecutive, it means that they need to happen in two different instances. What is the intuition behind this constraint? The intuition is that, so we are sending a broadcast, so a message that is visible to everybody, and we wait till all the participants retrieve this message. Now, if a second message arrives, what is the meaning? Shall we erase the first one? So there are some policies in synchronous reactive programming where you can collect all the messages, and maybe you take the maximal one, maybe you take the sum. So we go for the easiest way because this is a sort of an orthogonal principle. So we say that we just broadcast once, and if we need to send another message, that message will need to wait the subsequent event. So it means we send a message, and then if we need to send again, we are suspended. So we cannot evolve anymore. On the other way around, if we want to receive twice, it doesn't make much sense to receive twice the same message. So it means that if we have already received the message from the participant that we are interested in, then we cannot evolve anymore to receive the second time because we will need to wait for the new value to arrive. We can emit as many events as we want. So an event will be signaling something that has happened. So, and we will use it as a way of branching in some sense. And then when do we react to those events? When when we switch instant, then we will take a look at the events that have been emitted, and everybody, all the participants, will switch to an alternative behavior if the event was concerning the behavior of that participant. So, example that should be quite known to everybody. So if you ever use eBay, so electronic auction, we have an auctioneer that offers a good for sale, and several buyers that can compete on this sale, on this good, sorry. And the auctioneer will supervise the bidding and decrease the knockdown price. So some additional hypotheses just to make the setting easier for us. So we have one auctioneer and bidders, and one instant, one logical instant, will represent a bidding round, meaning that during the round, all of the bidders will send their bids, and the auctioneer will reply with the maximum. And as soon as a standstill is received, then the auctioneer would say, okay, we have a winner. And then some few additional hypotheses. So we have that the starting price is the same for everybody. Each of the bidders has a maximal budget, because otherwise we will have infinite loops. And these two hypotheses here are just for us so that we know who is the winner. But they can be relaxed just by making the protocol a bit more complex. So what is the behavior of the protocol? So let's forget for a moment for the colored parts. So this is the global behavior. We have that each of the bidders, bi to bn, will send their bid to the auctioneer, and then the auctioneer will reply with the maximum. And the idea is at a certain point, we will decree a winner, and then we will end. So this watch construct that you see here is the way of interpreting this event handling. So there will be somebody emitting an event saying that the auction has finished, and when this event is catched, we will move to this alternative behavior where the auctioneer will decree who is the winner. So we have broadcast, as I said, but from the point of view of the global type, they are actually just the usual multicast outputs. So we mark who is the sender and who are the intended recipients. And then there is another construct. There is this pause construct. So we will see that in the type construction, we will make the instance slicing explicit. So this pause means that every time we recurse, we stop the bidding round, and we start a new round, a new logical instant. So I'll just show you the implementation of the auctioneer. So recursion is the usual thing. We just need a parametric recursion because we need to remember what was the bids, what were the bids that we've seen before. But the idea is that if we receive the same bid as before, we have finished. Otherwise, we just communicate the maximum here. If we have reached a standstill, then we emit this event. We have finished. So this is this event. And in that case, at the next instant, all of the participants, so the auctioneer and the bidders, will arrive to this alternative behavior that is the end of the auction. And they will, this end bidded, so they will be notified of who is the winner. So as you can see, the green, bluish thing of the emit is actually transparent from the point of view of the global type. So we don't care about event emissions in the global type, but they do present in the implementation. So summing up, what do we have? From the session point of view, we have input, recursion, these if-then-else constructs. From the synchronous reactive programming, we have the pauses. So the pauses are explicit way of saying, I've finished computing, let's wait the next instant. The event emission, so we can emit as many events as we want. And this event handler that takes a role in the computation when we go from one instant to the next one. I put broadcast in the middle because it wasn't, it is a feature of synchronous reactive programming, but it's not just present in synchronous reactive programming, so it's something in the middle between the two. And from the type point of view, it's not really problematic. As I told you, we treat that as a multicast at the end, so it didn't change much the complexity of the typing system. So, what are the semantics? Obviously, we have a configuration where we have our process, as usually, the memory where we store the messages, so it's a sort of shared memory where the messages are stored, and we also remember who is the participant that sent the message, and what are the participants that read that message, because we need to remember not to read twice the same message. And we have this environment E, that is the environment storing the events. Since we have this, not just the process reduction, but this passing of a logical instant, we also need a new kind of reduction, that is the tick reduction. So let me just give you two examples that are very easy, the things that I will just point out, things that I already mentioned. So this is the reception rule. So as you see, we check, let me see if I, no, not working. So, as you can see, we just check that our participant is not present in the set of participants that has already read the message. So a reception can only happen if we haven't already read that message. And this is another interesting rule, that is the rule about recursion. And the idea here is that whenever we arrive to the recursive point, we have to finish, this has to be one logical instant. So we run till the recursion point, we pause, and then at the next round, and next instant, we can resume recursion. And this is actually the key part to prove that we have bounded reactivity. Because if we didn't have this, then recursion can possibly be an infinite. So this is the key point, and that's why I wanted to put it out here. And this is also why we need to have that pause in the global type before the recursive variable. So for the tick reduction, this is a bit more interesting because it's a bit more unusual to the community. So the idea that I said is that we can compute, so the process reduction goes on till all of the processes are suspended. So they can't evolve anymore. What does it mean? That we need to be able to identify that all of the processes are suspended. And this is the role of the suspension operator. This suspension operator will check if there are two subsequent sent, so in that case we are paused, or two subsequent, or a pending reception, so we are waiting for a message that is not in the store, or an explicit pause. If we are in one of these three cases, then the whole network of participants is suspended, and therefore we can move to the following instant. So what does it happen when we move to the next instant? The idea is that, first of all, we will empty the memory, so that we will prepare to the next instant and to the new messages that can be broadcast. We also empty the event environment, so we will receive new events and we can react to new signals. And concerning the network, the thing that we do is that, first of all, we remove all the pauses, and then we react to events. So what does it mean? Remember the watch construct. So for the watch construct, we just take, if we find the event guarding the watch, it's just a try-catch, it's not so new as a concept. So if you find the event, then we replace the behavior with the finally behavior. So the typing system. The typing system, I won't get into details concerning communication, nothing new there. The things that are new are actually the event handler and the instance slicing. So the instance slicing is explicit. We need to mark all of the pauses in the global type. As I told you before, we don't care about event emission, but we do care about alternative behaviors. In some sense, it's a sort of an if-then-else, so we need to track the normal behavior and the alternative behavior. So to give you an idea, so the first one is a process that is suspended because it has to send twice. So when we type a process, we also need to carry on the memory, because otherwise we don't have any information about what are the messages that have been sent and what are the participants that have already read from a process or not. So in this case, as you can see in the memory, we have that the participant P has already sent a message. So in order to type this, so the usual thing will be to have just the usual type. So send a message of type S and then proceed with the following. And since we have already sent something, we need to add a pause on top. And concerning the watch operation, so we just type the two branches, and then we record the fact that we have this alternative behavior in the type. We record this event here just to prove then subject reduction. So what do we guarantee? We have the usual guarantees of session types. Since we are based on the session types framework, we have the usual things that we prove in a session type. But then, what about progress? On one side, we have this bounded reactivity property. This is one part of the progress. But the point is that we could have live locks. So we have a process that is suspended because of a reception without the good send, and so we can go on instant through instance, just waiting for this send to appear. So what we prove for the typing point of view is that every input will be either matched in the current instant or in the next one. So again, it's a progress property, but adapted to our setting. And finally, you can play around with the setting, and you can add things that make the typing system quite complicated. But suppose that you need to have a scenario where you need that all the participants at each instance say, I'm alive, I'm alive, I'm alive, I'm alive, by sending something. Then we have also some machinery to prove this output persistence that forces the processes to send events at each instant. But it complicates quite a lot the typing system, so I won't present this now. So summing up, we have this reactive marriage with session types, and the interesting part is that we have these new two properties: the bounded reactivity, that is a semantic property, and the input timeliness, that is a typing property. And about open problems, so I didn't mention anything about delegation and branching, so we didn't go much into the delegation part, but we start thinking about the branching, and actually it seems that we can encode the branching with the watch construct. So it seems that we won't need the branching in our scenario. And then one can play around and say, okay, but what if we want to track events also in the typing system? Is it reasonable? Are there any properties that can match? I mean, there are significant in the setting of considering events inside of the typing system. So can we do something about this information or not? And what about pauses? So we did slice fix the slicing of time in the global type. Can we relax or not this hypothesis? I mean, there are a lot of questions that can arise from the typing system that we create. I didn't put a link on a technical report, but there is a technical report around, so just type multi-party reactive session and you will end up on the technical report. So thanks for your attention, and if you have questions.
Thank you, Cinzia. Any questions?
talk. All right. So thanks for the talk. First thing, technical report. Is that, I Googled it right now, but I found something from 2019. Is that the correct
Yes,
one?
is that the old version? Now we are working on a
Okay.
refined version where we don't have output persistence, so we clean up a bit.
Okay.
So it is the same thing. It is the same, at least the same syntactical thing without output persistence.
Okay, so but that's the thing that I
Yes.
should look at. Okay, then I have a question. I'm not sure whether I got the right intuition for logical instant. Maybe that's something that I should know, but I don't know. So what is meant by it?
So we don't have a clock that is timing the real duration of the instant. So the real duration of the instant is that we let all the participants evolve, doing their whatever they want to do, possibly 3,000 actions, and then when they all arrive to a suspension point, and the suspension is this explicit pause that is written in the code, this double send or this double reception or pending reception, when everybody has arrived to this situation, then we evolve to the next instant.
Okay, yeah, I wasn't quite, I didn't get that, but now I understand. I thought
Okay.
whether it was tied to recursion, but it's really tied to this pause in the code. Is that correct?
No, but you just said this is really tied in the code.
Yes.
Yes, exactly, yeah.
With a synchronization barrier for events.
Yes, right, okay, yeah, so I was thinking, like, I could also think in terms of a transaction, kind of.
Yeah, in
may
some
I-
sense, yes.
May I ask another question? How do I read the typing judgment? There was a slide with 2 typing rules, and you said,
yes.
referred to the memory, and I wasn't sure which part it was. And then there's a subscript on the turnstile P, and I wasn't sure, does that
Yes,
denote a participant or?
Wait, because it's not responding as I want. Okay.
Yeah, this, exactly.
So here I'm typing a process. So this P means that I'm typing participant P.
Okay.
In this environment that just gives me information about the
Yeah.
sort of the messages. And then I'm typing this configuration where I have the process and the memory.
So the comma M, after the P comma, so the M union P, that's the memory, is that?
Yes.
Okay, good.
This is the memory,
Okay,
and this is the type.
okay, thank you so much.
Okay, Hans, another question.
Thank you. Just out of curiosity, because you involve broadcast in your language, but there's a dual notion called, I think it's called gathering or collection, where broadcast is one-to-many, collection is many-to-one. And I'm just wondering, you would probably want a similar property if you have collection instead. How easy do you think it would be to adapt your setting to that operator?
So I didn't think about this, but I don't think there would be a problem because the main problems come from recursion and pauses. So the communication for us is quite transparent. So I wouldn't say that poses a problem. But then, I mean, you need to look into details, and when looking into details, problems can come up. But I think that we can have a similar treatment. But I don't know, because so something, it's not really, I really didn't think about this, but reading from many, so it means that you need to do some operation on the values because you need to collect one value at the end. So it could be something that is handled by the semantics, I would say. So from the typing system, I would say that it should be quite transparent. It should be.
Okay.
I don't know if you have further comments.
I think it's philosophically different in the sense that I know that this broadcast and gathering mainly coming from parallel architecture, right? You have these parallel architectures in which you do this and that. But the broadcast here is mostly like a philosophical choice on the programming model that comes from synchronous reactive programming, right? That's the only way of contacting which you would like to have different processes. So I do agree with Cinzia that there should be some way of accommodating that, but it looks like like hard to fit. But I don't know if Ilaria would like to add something.
Yeah, actually, in our so maybe first thing I wanted to add for Stephanie is that the notion of logical instant actually comes. It's not an original notion we introduced. It comes from the family of synchronous languages that was developed in France since 40 years in the ST30 family. Actually, this synchronous reactive programming is a simplified form of ST30, where you have, delayed reaction to the absence of an event. That's a bit technical. And concerning Hans' question, so in our broadcast, the threads, the participants are not forced to read a message. They only read it if they need it. And in what you suggest, is the recipient obliged to receive messages from everyone or not?
No obligation.
No obligation. So I think that could be dealt with quite easily, yes. And because, okay, maybe we can discuss it offline.
Well, there's also, let's take Matt's other question, final.
Yeah, but
Hi, thanks for the talk. So my question is, in one of the first slides, you showed the example with of the bidding.
Yes.
And I noticed you quantified the bidders with some subscript n. Yes. So I want to ask, is this n a known value? So when you write the protocol, you have to be aware of the full number of participants.
Yes.
Okay. And are you interested in looking to see how you can make a bidder or server agnostic of this? Because if we look at systems like eBay, like you said, you don't know how many people are bidding.
Indeed, I think this is an orthogonal problem. I think that there are families of session type where you don't know at the beginning the number of participants. So you have the, let's say, the global protocol, and then some of the participants join, and then when everybody has joined, then you start the protocol. But I would say that this is an orthogonal thing. So we didn't consider that setting here because we already had enough problems with the poses and the time. So we had to simplify as much as possible.
Okay. Thank you.
I would add, something. This is a well-known problem in synchronous, in these synchronous languages. They are not modular, actually.
Yeah.
Because to decide suspension, you have to know who are the threads.
Oh, right.
So
that's also
be a trivial extension.
no, I don't think so.
Yeah, but when you set the protocol, then you have the network, and the network is fixed.
Okay, if we had some mean of doing a poll to know who is there, then we know who to check at the end of the instance. But we have to know who are the participants.
Yeah, but it's clear that the tick reduction is a global property, so it's not compositional.
Okay, that takes us up to time, so thank you again, Cinzia.